Okay, so the second type of polymer that we're going to be looking at is called a condensation polymer. So this is where we, to link up our polymer, so we've looked at addition reactions, which is where you have a carbon-carbon linkage. Condensation polymers is where you either have a carbon-oxygen or you have a carbon-nitrogen link. So condensation reactions that we're referring to when we do these polymers is actually the same ones that we saw to form esters and to form amides. So when we create a condensation polymer using an esterification reaction, it's known as a polyester, the same ones that are probably in your pants, your uniform pants. And when you have it forming an amide, it is a polyamide. Okay, so we're going to go through both types of reactions. So the monomer, we'll look at polyesters here first. The monomer that's used when you create a polymer is different from when you're making a regular ester. So let's go back for a second, right? To make an ester, you need a carboxylic acid and you need an alcohol. Okay, so let's say we have something like this. So if you were to do this reaction, this would make an ester, right? The OH and this H would be making water. And then, of course, we would have this link up here. However, that would really be the end of the chain. In order for a polymer to be made, you need to have carboxyl groups either on, on either end of this structure. So in that case, now we're able to have the reaction happening on both sides. Remember, the goal is to create long chains. You have to have a functional group that's reacting on either end, so that way we can continue the chain this way as well as this way. And same thing for the alcohol. You need to have an OH group at either end of the molecule, again, so that it can link on either side to create these polymers. So going back to this, the monomer that you use for a polyester has to have a dicarboxylic acid. So it needs a carboxyl group at the end of each end of the molecule, and a diol. The OH group has to be at the end of each end of the molecule. So what ends up happening is you have an ester linkage that is formed on either end, and that will continue it to grow. The chain will grow on either side. So of course, just like any other ester reaction, and actually amides are going to be the same, the reason why they're called a condensation reaction sometimes is because water is also made as a product, and nothing has changed otherwise here, the same deal. So this picture down here kind of shows you what's happening, right? So here you have your carboxyls on either end. So this blue rectangle can mean that you can have any number of carbons here. So this can be, 6 carbons in length, 7 carbons in length. It doesn't matter. What matters is you need a carboxyl on either end. Same thing with the alcohol. You can have multiple carbons in between, but what matters is to make the linkage on either end, you need to have an OH group. So what ends up happening is you have the connections being made, and you have your originating carboxylic acid portion and your original alcohol portion. And then, of course, maybe we'll use a different color here. This is where your ester is. With, of course, multiple waters would be made. Okay, so I find this is easiest to see when we write it out as an example. So this is using, the note goes through just looking at symbols. So it's like, we can talk about it, but it's kind of just a representation. So if you have 2 triangles that are representing the 2 carboxyl groups and the 2 little circles representing the alcohol groups, when you form your polyester, you're going to have it alternating. So it's going to be triangle, circle, circle, triangle, triangle, circle, circle, triangle. I know, silly, but anyways, like I said, it's easier, I think, to see it as with an actual example. Of course, please read through the note. So let's take a look at, and I'm going to do different colors for the different substances. So I'll do red for our carboxyl groups. So we'll do this with 3 carbons. So this is really propane dioic acid. You don't need numbers because it's on either side. Plus, let's do a different color to represent the alcohol. And let's do 4. So we have an OH group and we have an OH group. All right, so this would be 1,4-butane diol. Okay, so obviously when you're doing, same with any other polymer, technically there's multiple of these monomers. These are considered to be monomers. So in a condensation polymer, you actually have 2 different monomers that are combining. So we're only showing 1 repeating unit, like 1 of the alcohol and 1 carboxylic acid, but really remember there's like hundreds of thousands of each of these, right? So what happens? I'll use a different color. The OH groups on the carboxylic acid and the H from the OH combine to make waters, right? So we know that waters will be made as a product. So when we connect these, there's going to be multiple connections. So just to show you like a repeating unit, I'll do multiples here. So let's take a look. Okay, so this is now what the acid was with the OHs removed. So then you have oxygen, 1, 2, 3, 4, oxygen. Okay, so here is the alcohol with the hydrogens removed, right? And then of course, this is our ester, right? So you have to imagine on this side, there would be another alcohol group. So on this side, there's another acid group. So I'm going to show a second unit so you can see this. Right? So here's my second acid. Here's my second alcohol. 1, 2, 3, 4. Right? So here are my esters. So you have to imagine you basically have repeating units of red, blue, red, blue, red, blue. Like on this side, there would be another blue. On this other side, there would be another red. And you would just continue alternating. So however, if we wanted to show just 1 repeating unit, typically what we would do is we would have this. And then 1, 2, 3, 4 with our oxygen and a line. Right? So showing that on this side is where the connection would be of the next monomer. Here is where the other monomer would be. Now, when you're doing the polymer naming, so it's funny, let's name what the ester would be with these 2. Let's say we were making 1 ester. This would be really butyl space propanoic acid. Right? So the butyl is from the alcohol. The propanoic acid, oh, pardon me, oh my goodness, it would be propanoic acid. Propanoate, whew. It's an ester, hello. Okay, so butyl propanoate. So that is what it would be if we were to make 1 ester. So the name for this polymer is literally just with poly in front. Polybutyl propanoate. It is automatically assumed that to make a polymer ester, you needed to have started with a dicarboxyl and a dioic acid. So when you're naming, so that's a difference between what we've looked at already and these new condensation polymers. Before, the polymer name was based on the monomer unit. In this case, the polymer name is based on what the actual ester name would have been. And the next one we're going to look at with the amide, the polyamide, is exactly the same thing. Literally, the only difference is instead of being a C double bond O with an oxygen here, this would be with a nitrogen. That's the process of this, everything we just talked about is exactly the same, except we have, instead of having a diol, we have a diamine, because you need an N group on either end of the molecule. So let's take a look. So here we have a polyamide. Okay, so polyamides is where you have monomers. So again, two different types of monomers. A dicarboxylic acid, so you need a carboxyl group on either end, as well as a diamine. So the amine group has to be on either end of the molecule as well. So, and you can see this here as well. So what ends up happening is, right, your polyamide is alternating carboxylic acid and amine groups. And then, of course, here's the amide linkage. So here we have hexane dioic acid. So there's carboxyls on either end on carbon 1 and carbon 6. Here we have 1,6-diaminohexane. And you'll notice here, and this should also be plus water as I'm noticing. So you have your carboxyl group and your amino group. So you have to remember on this side, you would have another amine group. And then on this side, you would have to imagine, right, you'd have another carboxyl group. So polyamides are also sometimes referred to as the term nylon, followed by two numbers. So again, this is not an official IUPAC name. Your IUPAC name always goes by naming the amide and then, of course, having the word poly in front. So this would actually be polyhexyl, right, because there's 6 on the amine group. And then this would be 6 again. So this would be hexanamide. Okay, and then you just put poly in front, similar to the ester. But if you look at a name that says nylon and then there's a number, comma, number. So the first number is always referring to the number of carbons on the diamine. The second number is the number of carbons on the dioic acid. So nylon 6 means a hexyl group for each one. But let's say we had nylon 3,2. I don't know, I'm just making it up. This would mean that you would have an amine with 3 carbons on it, and your carboxyl group would have only 2 carbons in length. It'd be like a ethanoic acid or dioic acid. So nylon, when I ask you for the name of your polymer, I always want the IUPAC name. But if you read or come across, I do expect you to know the order and what the numbers represent. So if you're told nylon, 3,2, to go about drawing that or understand the meaning of that, you should be able to do that. Now, we haven't talked about intermolecular forces here yet, but both polyamides and polyesters have, actually more so polyamides, they have hydrogen bonding. So polyamides are actually incredibly strong in terms of their intermolecular forces, because what happens is you have these big long chains, not only of the strong covalent bonds with the polymer itself, but also with the intermolecular forces. So, for example, polyamides can be, once they've been cross-linked, I should say, cross-linking again adds even more strength, are used essentially in a material known as Kevlar, which you may sound familiar because it's used in bulletproof vests. Maybe you watch like a movie or a TV show where they have that. So hydrogen, this strong network of hydrogen bonding causes it to be an incredibly dense, strong material. The other types of polymers that are very familiar are polymethyl acrylate, which is not a formal name, but it's the material that is very absorbent that is in diapers. So they're able to absorb water due to their polarity and keep the baby or adult, dry. You never know when we're going to need what we need.